Welcome back. In this video, we continue our discussion of 3.1, Introducing the Derivative. In day 1, we looked at the derivative at a point. And the idea is, if you have the graph of a function f, and you have some x value a, you can find a tangent line to the graph of f at the point where x equals a, and the slope of that tangent line is denoted f prime of a. That is the derivative at a. Now, this f prime, that is a different kind of function. F is a function and f prime is a function. So we want to know, how do I figure out the function f prime of x? And that's what this video is all about. So this video, 3.1 day 2, the derivative function, computing the derivative function. Recall, we had a way of computing the derivative at a point. I called it the h approaches 0 form. And f prime of a equals the limit as h goes to 0 of f of a plus h minus f of a all over h. You can see the diagram down below that shows where this idea came from. We look at the slope of a secant line, and then as h approaches 0, that secant line turns into a tangent line, and we end up with the slope of the tangent line. Well, what would happen in this expression if I replace a with x? That's what I get. And suddenly there's a new kind of perspective. I'm not just talking about f prime of a, I'm not just talking about the derivative at a point. Now I'm looking at the derivative function, f prime of x. And this is how the derivative function is defined. Let's take a look at a graphical representation of this. In this picture, as I move x, I can see the tangent line, and on the right I see that f prime of certain x values are certain slopes. So this tangent line has a slope negative 1.54. As I move to the right, I put my x on 3, f prime of 3 is negative 0.57, so the slope of the tangent line is negative 0.57, and so on. So we can see how the tangent line changes as I move my x, and correspondingly the slope of that line is changing also. Well, what if I actually plotted a comma f prime of a? Now you see an orange point in the plane, and as I move, the height of that point is the slope of the tangent line. So when x is 1, the slope of the line, the slope of the tangent line is 0.45, and the value of the orange point is 0.45. When x is 2, the slope of the tangent line is negative 1.54, and the value of that point is negative 1.54. And so on. As I move my x, we can see how the value, that is the height of that point, reflects the slope of the tangent line. Well, then finally, I actually want to trace that point. Here we go. And the curve that I end up with, that is the graph of the derivative function. That is the graph of f prime of x. So see how the derivative function works. For example, at 1, the value of the derivative function looks like it's about 1/2. And if I look at the actual curve, oh yeah, the original function has a slope of about 1/2 at that point. Now, when x was 2, the value of f prime, the derivative function, the value is about negative 1.5. And if I look at my original curve, I can imagine a tangent line when x equals 2, and the slope of that tangent line will be about negative 1.5. All right, returning to our discussion on the slides. So let's actually compute a derivative. We'll let f of x be x squared, and we'll use this formula to compute f prime of x. Here we go. Claim, if f of x equals x squared, then f prime of x equals 2x. So the derivative function is 2x. So I always start with the definition of f prime of x. F prime of x is the limit as h goes to 0, f of x plus h minus f of x divided by h. Now let's take that numerator and we'll simplify that for a little bit. So I like to pull that off to the side and work with that. So f of x plus h minus f of x is x plus h squared minus x squared, because remember, our function is f of x equals x squared, so f of anything is that thing squared. F of x plus h is x plus h squared. Let's expand the square, and I can simplify by seeing that those x squareds fall out, and then maybe I'll factor out an h. Okay, be sure you pause the video and see that, if you need to, and see that you understand all of these steps. Now, my goal, I didn't say this before, but my goal was actually to find an expression that has a factor of h in it. And I did. Look at that. I have a factor of h. And that's nice because when I plug it back in to my expression, now I have a factor of h on top and that h on the bottom. So the factors of h cancel, and I'm left with the limit as h goes to 0 of 2x plus h. And that's something I can easily calculate. I can really just plug in 0 now for h and get my answer, which is 2x. And so it works. If my function f is x squared, then the derivative function is 2x. So there are three basic examples, three basic functions that we will see their derivatives again and again and again. The first one we just did. If f of x equals x squared, then the derivative is 2x. If f of x equals 1 over x, then its derivative is negative 1 over x squared. And if my function is the square root of x, then its derivative is 1 over twice the square root of x. Now, in a moment, sort of on the next two slides, I will go through the proofs of these formulas, just like I did on the previous slide for x squared and showing that its derivative was 2x. But what I want you to do is pause the video and really try to write out those proofs yourself before you see me do them. It is a great exercise. Just real quick, one last word before you do that, a word about notation. D over dx is one way of saying the derivative. So this first expression, I read this as the derivative of x squared is 2x. In the next one, the derivative of 1 over x is negative 1 over x squared. And then the derivative of square root of x is 1 over twice the square root of x. This d over dx notation is nice because we don't have to declare a name for our function and then take the derivative. I can just do it all at once. Okay, so like I said, at this point, pause the video, see if you can compute these derivatives, and then when you're ready to check your answer, unpause and check my work on the next slides. Go to it. Example 2. Let's show that the derivative of 1 over x is negative 1 over x squared. So f of x is 1 over x. F prime of x is defined this way. Let's take out that numerator and we'll start simplifying the numerator. F of x plus h is 1 over x plus h. F of x is 1 over x. I need a common denominator, and the common denominator of x times x plus h works. Now this next step, this is where everybody makes an algebra mistake. I need to subtract the quantity x plus h so that negative distributes. When I combine the fractions, I get x minus h. Oh, but those x's fall away, and I'm left with negative h divided by x times x plus h. So now, in my limit problem, coming back to the limit problem, I can take that h that was in the denominator, and I express that as a multiplication. So I get the limit as h goes to 0 of 1 over h times negative h over x times x plus h. And I have the h's that cancel. That leaves me with the limit as h goes to 0 of negative 1 over x times x plus h. And now I really can plug in 0 for h. And when I do, I get negative 1 over x squared. See how the limit expression disappeared in that last step? Some people miss that. Some people keep writing limit, 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 but don't forget, in this last step, that's when I actually take the limit. So my penultimate step here, it means take the limit of this expression. So I do take the limit, and now that LIM disappears, and I'm left with the answer. Let's take a look at our final function. If f of x equals the square root of x, then its derivative is 1 over twice the square root of x. Let's prove that. F of x, I always write out the definition at the beginning. It's good to set yourself on the right path. F prime of x equals the limit as h goes to 0 of f of x plus h minus f of x all over h. Let's look at that numerator more closely. F of x plus h minus f of x. Well, my function is the square root, so that's the square root of x plus h minus the square root of x. At this point, it feels like a dead end, but there's a trick, and it really is just a trick that often comes up with square roots. I can multiply the top and the bottom by the conjugate. So the conjugate of this expression is the square root of x plus h plus the square root of x. So I'll multiply the top and the bottom, so it's just kind of the same expression on the top and the bottom, so that whole fraction is just 1. I'm not actually changing anything, I'm only changing how it looks. And when I expand the numerator, I get a really nice simplification. It just turns into x plus h minus x, and that new denominator stays there. Oh, but look, in the numerator, those x's fall away, and I'm left with just h over square root of x plus h plus square root of x. So again, I will take the h in the denominator and express it as a multiplication times 1 over h. And I see I have a common factor of h in the denominator and the numerator, so those cancel. And I'm left with the limit as h goes to 0 of 1 over the square root of x plus h plus the square root of x. And now I can plug in 0 for h. And when I do, I get 1 over square root of x plus the square root of x, and that becomes 1 over twice the square root of x. Alright, so this finishes 3.1, Introduction to the Derivative. I do want to emphasize the importance of this derivative definition. Some of you who have taken calculus already might be looking at these three functions and you say, hey, I know those derivatives already. I know that there's a certain trick that you can do to get the derivatives. And that's true. We will see shortly that there are some tricks that you can do to figure out derivatives quickly. But it's really important that all those tricks come from the fact that this is the derivative. Every derivative we take in this class has its foundation in this definition. So it's definitely worth, at this point, understanding how that definition works and being able to derive a few functions using it. All right, that ends 3.1.